All right, guys, good morning. I did a fault video the other day, so I'm just going to let you know where you can actually find it. It's on Blackboard for my on-campus lab class. It's under the lab exercises. And in fact, I think for all of my lab classes, I put it under the lab exercises. So you'll see it, it'll say dip slip and strike slip fault identification video. For my lecture classes, both online and on campus, it's under the lecture note link. So if you're wanting to know how to identify faults, dip slip faults and strike slip faults, just go to Blackboard, go under those links on Blackboard, and you'll find the video. I'm going to do a video on relative dating today because I think sometimes this might be confusing. And when you look at the puzzles and the exercises, sometimes they're overwhelming, especially if you haven't seen them before. So I'm going to start off and just kind of give you an idea what relative dating is. It's something that we can actually do out in the field very, very easily. You don't have to know anything about the rock unit you're looking at. You don't have to have been in the area before or anything. And pretty much what relative dating is when we actually look at the rock layers, we can determine which rock layers are older and younger just by the way they're sitting out in the field. So in order to understand that, there's some relative dating laws and principles that we actually abide by. So I'm going to explain those first, and then I'm going to actually do a relative dating diagram with you so that you'll know how to complete the exercises that are on Blackboard for you. So the first one I'm going to show you right here is called the principle of original horizontality, and you can see that on this worksheet right here. And pretty much what it states is when sediment's deposited in a water environment and turns into sedimentary rock, as geologists, we always assume that those rock layers are going to be nice and horizontal with each other. So if I drew a picture of an outcrop that we're looking at outside, and I had, let's say, 4 rock layers here, 1, 2, 3, and 4, you can see that they're nice and horizontal with each other. So this abides by the principle of original horizontality. Now, as we've talked about with plate tectonics and things like that, a lot of rock layers aren't nice and horizontal anymore. They become folded over time, and we have to determine why they become folded over time and what events these rocks actually were put through in order for them to become folded. So this is the simple one right here, the principle of original horizontality. It's pretty straightforward and easy to understand. The next one's the law of superposition. So again, I'm just going to use my diagram right here. This is layer 1, 2, 3, and 4. What the law of superposition states is that in an undeformed sequence of rocks that are horizontal, the oldest rock layers are on the bottom and the youngest rock layers are on the top. So you can think of it as a stacking relationship. So sediment layer 1 was deposited, 2 was deposited next, 3 was deposited next, and finally 4 was deposited. So in this sequence right here, which is very simple, 1 would be the oldest and 4 would be the youngest in the sequence. And that's the law of superposition. I'm going to skip to another one on this sheet, and then I'll go back to the inclusions. But I think the most important one is the principle of cross-cutting relationships, because that involves faults, intrusions, things such as that actually cut through the rocks and help us relatively date the sequence that we're looking at. So I'm going to use one of the examples that was in the fault exercise and the fault video that I went over the other day. So I'm just going to draw a simple fault. And again, this is an outcrop view. All of the pictures that you'll see in the relative dating exercise are going to be outcrop views. So treat them that way. And what that means is if you see a fault on the diagram, it's going to be either a normal or a reverse fault according to our dip slip ideas that I went over the other day in the video. So I'm going to draw a fault right here cutting through these rock layers, and I'm going to draw 4 rock layers again. So I got layer 1, 2, 3, and 4. I'm going to draw 4 rock layers over here also. Okay, so there's layer 1, there's layer 2, there's layer 3, and then there's a little piece of layer 4 right there. So you can see again, just like in the video the other day, our rock layers are offset. So the idea is that if we see a fault or if we see an intrusion cutting through the rock layers, that fault or intrusion is younger than the rock layers that it cuts through because those rock layers have to be deposited and formed first. So what we can do now is we could say 1 was deposited, 2 was deposited, 3 was deposited, 4 was deposited, and finally the fault cut through layers 1, 2, 3, and 4 because we see that offset and all 4 rock layers have been affected. That's the principle of cross-cutting relationships. So if I put, let's say, a big intrusion in this, So let's say here's a big igneous rock intrusion. And what that means is magma has cut through the rock layers and eventually has turned into an igneous intrusion. We call those intrusions. So you can see it cut through layers 1, 2, 3, and 4 on the left, but it only cuts through layers 1 and 2 over here. But you can see it cuts through the fault also. So relative age-wise, even though this rock layer over here, the intrusion, might not cut through the rock layers on the right, we still know the relative age of it because it cut through this fault, and the fault cut through all the rock layers first. So what we could do is we could say oldest to youngest in a sequence, and I always start from the bottom and work my way up to the top. And then you want to put down the numbers or the fault or the intrusion or what have you that's in your diagram in that relative sequence. So we can say 1 was deposited, 2 was deposited, 3 was deposited, 4 was deposited, faulting occurred. Okay, so we have our fault. And then finally we have our intrusion, which is the youngest in our diagram. Okay, so that's probably the most important, I believe, principle/law of relative dating. Let's go back to the principle of inclusions. And this one's actually pretty easy. And it goes along with the other one, which is the principle of unconformities, which can be kind of complicated at times. But let's do the easy one first, which is the principle of inclusions. Let's say we have these 4 rock layers. Okay, so I'm going to say layers 1 and layer 2 were deposited. Okay, and let's say layer 3 and 4 aren't formed yet. So we had layer 1 and 2 deposited, and this again is in a water environment. So these sediments are covered up by water. So let's say the sea level changes where the water drops, and you have weathering and erosion occurring on top of your rock layer. So the top of layer number 2 right here is going to be weathered and eroded. So there's going to be a nice uneven surface on the top of rock layer number 2. And again, this is 1 and 2. We call this an unconformity. Okay, and an unconformity is just basically a weathering and erosion surface, so that if the sea level rises again and we have sediment deposited on top of layer 2, let's say we have 3 and 4 deposited now, we have actually preserved that unconformity between layers 2 and 3. And what that tells us in the geologic past is that the sea level dropped so that the top of layer number 2 could be weathered and eroded, and then we had a rise in sea level again, and then 3 and 4 were deposited on top of 1 and 2. So again, this kind of traps in that unconformity, and this kind of gives us an idea about the history of the environment when we look at the rock layers. So in a sense, for the principle of inclusions right here, I'll go back to the unconformities again in just a second, but again, the inclusions and the unconformities kind of go hand in hand. But a while ago, I had 1 and 2 deposited, the top of 2 was weathered and eroded, and let's say pieces of 2 were deposited on top of itself. So again, think of it as, let's say, sandpaper on wood. You sandpaper the top of the wood, and you're going to have sawdust and fragments of wood on top of the wood itself. So you have fragments and pieces of layer number 2 on top of itself, so that when 3 comes into the area and forms, those pieces are trapped inside of layer number 3. Those are called inclusions. And inclusions are pieces of an older rock unit inside of a younger rock unit. So again, you can see relative dating wise right here, this is a simple sequence, 1, 2, 3, and 4. But the inclusions still help you determine sometimes which layers are older and younger, because again, the inclusions are older pieces inside of a younger unit. So pretty straightforward there. Getting back to the unconformity right here, I'm going to draw this picture again with all 4 rock layers. So here's my unconformity. Here's my weathering and erosion surface. This was layer 1, this was layer 2, this was layer 3, and this is layer 4. When we identify unconformities out in the field, we have different types of unconformities. So I want to show you that in this picture right here. Okay, and you can see there's an angular unconformity, a disconformity, and a nonconformity. And the relationship of the rock layers above and below the unconformity helps us to determine what type of unconformity we're looking at. So in a simple one like this, where we still have nice horizontal sedimentary rock layers, and you can see the unconformity between layer 2 and 3, by definition, this would be a specific type of unconformity called a disconformity. Okay, so if you ever see sedimentary on top of sedimentary with the unconformity wedged or sandwiched in between them, we call that a disconformity. And you can see that right here on this diagram. So this is limestone, this is sandstone. They're both sedimentary rock layers, and you have your unconformity wedged in between them. So by definition, that's a disconformity. And this is what it would look like out in an outcrop of the field. So here's our sedimentary rock, and here is our disconformity right there, okay? Now, the nonconformity is a little bit different, and I'm gonna get another sheet of paper to show you the nonconformity. And actually, let's go back to the old paper first. Okay, so we're gonna do a before and after. So let's say we have 2 rock layers deposited in an environment, and we have a huge, massive intrusion, igneous rock, that has cut through layers 1 and 2. Okay, let's just number these. So relative dating wise, we already know the intrusion is younger than 1 and 2 because it cuts through layers 1 and 2. But let's say we have weathering and erosion on top of layer 2 and on top of that intrusion right there. So that when we draw our final product of the 4 layers, okay, we have our weathering and erosion surface right here. Okay, here's my intrusion. This is 1 and this is 2. And then we have 3 and 4 on top of it, let's say, just like we did in the other drawings. Okay, so 1 and 2 were deposited, the intrusion occurred, and then finally 3 and 4 were deposited on top of it. That would be the relative sequence, okay? But you'll notice that this is igneous rock. Let's say this is granite, okay? And from here to here, we have granite below and we have sedimentary rock on top. If you have igneous rock or metamorphic rock below your unconformity and you have sedimentary rock on top of it, that is called a nonconformity. Okay, and you can see that in this picture right here. So they had igneous and metamorphic rocks under the unconformity, and then they had sedimentary rocks on top of it. So by definition, it's a nonconformity. And you can see in the diagram too that there are inclusions, okay, which are the older pieces of probably the metamorphic rock below it and the limestone. So again, sometimes inclusions help us relatively date the diagram we're looking at. Finally, the last one I want to show you is an angular unconformity. So let's say we have 3 sedimentary layers deposited and then they become tilted. So we had some upward force applied to the side of the rocks, let's say our 3 rock layers. 1, 2, and 3, that causes them to become tilted over time. So I'm just going to draw them tilted now, okay? So they're not horizontal, they're tilted now. So that when weathering and erosion occurs, okay, it chops off part of layers 1, 2, and 3. So we might see something like this out in the field where we have our rock layers. Here's our unconformity. Okay, so this is layer 1, this is layer 2 and 3. And then on top of that, we might have layer 4, which is still nice and horizontal according to the principle of original horizontality. So if you have angled or tilted rock layers below your unconformity, and you have horizontal sedimentary rock layers or a layer above it, we call this an angular unconformity. Okay, and again, you can see that in the diagram right here. So we could say that something caused these rock layers to become tilted, and it was some type of upward force. So it kind of gives us, again, a history of the rocks and why they actually look like the way they do now instead of being nice and horizontal like they were originally. So you have your tilted and angled rock layers below, and you have your horizontal rock layers above. And you can see it right here. So right there would be my angular unconformity. So you have your tilted rock layers, then you have your horizontal above, okay? Now, to finish off the video, I'm gonna do an exercise with you really quick, and I'll go ahead and use the same sheet of paper on the back. This is one of the exercises I give my earth science class on campus. We actually do this in lab. So they're doing this online right now, just like everyone else is doing all their work online. But what I'm going to do is I'm going to show you how to relatively date this diagram right here. And the questions that you see below right here are actually associated with the diagram. But a lot of times I tell my students to relatively date the diagram first, so that when they see questions about, is Pluton A older than the fault H, true or false, then you can actually go back and look at your sequence and you can determine the answer very, very quickly. So again, what I'm going to do is I'm going to start at the bottom and I'm going to work my way up to the top of the drawing. So I'm going to go from oldest to youngest. Okay. And then I'm going to start with my layers, okay? And what you might want to do in a drawing such as this, since there's a lot of stuff here, is identify your faults and your intrusions first, and that kind of sets everything up for you. So you could say, here's fault H right here. So fault H is cutting through all of these rock layers right here, so we know that fault H is going to be younger than all of these rock layers. A cuts through all of those rock layers and these rock layers here. So we know A is going to be younger than all of this stuff right here. And then finally on top, we have 4 rock layers that are on top of A. So we know these rock layers are actually younger than all of this sequence here. One of the things that I do want to mention, when you see an unconformity, that kind of gives you a package to look at when you're relatively dating diagrams. So here's an unconformity here. So this is a package you could relatively date. This is a package you could relatively date together. This is a package, and then finally you have that top rock layer, which is the youngest in the sequence. So I'm just going to start by labeling my oldest first. So E, G, L, C, right? And then we have the fault. So we're going to call that fault H. That cuts through those rock layers. And when you come to this right here, you can see that A cuts through M, D, and J. So we know A came after those 3 rock layers. So M was deposited, D was deposited, J was deposited, and then finally we have intrusion A. And then it's easy from here. We have N, we have K, we have B, and then finally F on top. So see, so when they ask, is Pluton A older than formation N? Okay, well, Pluton A, which is right here, okay, and where's N? N is right here on top of it. So Pluton A is older than formation N because N is on top of A, right? So in our relative sequence, we can actually answer these questions pretty easily. Sometimes when you read the question and have to go back to the picture numerous times, it kind of gets confusing. I want to go back to this fault right here. We're going to identify what type of fault this is, and then we're going to identify the unconformities just to make sure that everybody's on the same page. So let's look at our fault. Okay, so I'm just going to draw my fault separately from all of this. So here's my fault in the picture, and I'm just going to draw one rock layer. Let's say G right here. So here's G over on the left side, and here's G, let's say, over on the right side. So this is either going to be a normal or a reverse fault according to what I showed you in my video the other day. So I'm going to do the same thing I did in my video, and I'm going to label my person or draw my person on my fault. So there's the dot in the center of the fault. There's that vertical line, head on top of the line, feet at the bottom of the line. And again, that naturally labels the head wall and foot wall for you. So his head is on the left, that's the head wall. His feet are on the right, that's the foot wall. And again, this is our marker bed right here, okay? So we can determine what side moved up and what side moved down. So if I just draw this again with the fault only, okay, and the head wall and foot wall labeled, we can actually see that the left side right here, okay, is lower than the right side. So the left side moved down and the right side moved up. So if you look at the definition, when the head wall moves down and the foot wall moves up, as I gave you, that would be a normal fault by definition, okay? Now, the unconformities are pretty easy and pretty straightforward. Let's look at the first one right here. And you can see that these rock layers are tilted, but they're still horizontal with each other. So they still abide by the horizontal rule, even though they're tilted when we identify what type of unconformity it is. So these are nice and horizontal rock layers on top and on the bottom of the unconformity. We're going to assume they're sedimentary rock layers. So we can say that this is a disconformity by definition. Sedimentary on top of sedimentary. Now, when we get to this one right here, which is at the base of layer M, you can see that there's horizontal rock layers above and they're tilted below. So that would be an angular unconformity by definition. When we get to this unconformity right here, you can see that these sedimentary rock layers, again, even though they're tilted, they're still horizontal with each other. So that would be a disconformity by definition. But I want to point something out to you right here. Look at this point and this point, this point and this point that come into contact with the base of N. That's where your igneous rock is. Okay, so At these two areas, we would call that type of unconformity a nonconformity by definition. So you can have different unconformities along your outcrop depending upon which rock layers are actually associated with the unconformity. And then finally at the top of right here, the base of F, you can see that this is a horizontal rock layer, abides by the original horizontality principle. And directly below it, we have angular rock layers. So this would be an angular unconformity by definition. Okay. So that's pretty much it with relative dating. Some of the puzzles get very, very complicated. Some of them are easy. But again, if you follow the rules and the ideas that I showed you in this video, you shouldn't have much problems doing the exercises and, figuring out what you want to do with regards to your relative dating diagram.